Okay, so I'm going to try to quickly walk you through some of the code I put into GitHub. So it is not exactly what was used to generate the images that were given to the big benchmark for human, because in this case we're looking at an 96 well plate. A plate was made of different well, A1, A2, A3, and each well were run separately. So here, this is a simpler version that will look at one single directory and process it. It will, and actually was generalized to allow not only the spot detection, but to do some other computation, looking at a multi-channel image. So before I go into the code, let me show you an example set that we have. So right now I am doing, I'm on radbio.arc.nasa.gov. To get there, I'm using RDP, the remote desktop option. And to get there, you need to be on VPN. So this is impossible for you to see until you have VPN. Now, I'm under /data, and then here under /data, let me go back. There's different wells. I'm going to use that well test. So I'm going to, here it's interesting what you see here. Go back. That .czi, this is the single, all these images actually are embedded into that one place when you take the image on a Zeiss microscope. And you can see the size of this is pretty big. It's almost 1 terabyte. It's 800, sorry. It's 8 gigabyte. I was like, that's huge. Okay. Now, this is similar content, but split into TIFF image. So that's typically what we work with. And from the microscope we use currently, and that changes all the time depending on the instrument. So that's why I wrote this script to be more, well, that script will still need to be adjusted based on the type of input. But just very quickly, let me walk you through the structure. So that's the name of the experiment here. And then these S are really, if you want, they are scene or field of view. So it's field of view 0, and then 1, and 2, and 3. So it's different field that we take, and field are pretty large typically. And you can see here that there were 4 channels taken. AF48, so that's typically green. DAPI, that's typically blue. And then what you can see right there already is that for this AF48, there was a Z stack taken. And so you can see it went to Z0, 1, 2, 3, 4, 5, up to 10. Then at 10, there's the AF48 that shows up. At 10, there is a 594 and a 647. And then AF48 continues afterwards. So I know it's a bit complex, but what it means is that there was a full Z stack taken for green only, from 0 all the way to 20. So it's 21 slices. And for the 3 other channel, DAPI, which is nucleus, which is blue, and then 594 and 647, those are different kind of red, from visible red to far red, where it's hard to see with your eyes. They took the middle section for that. So they took section number 10. Okay, it's to save space, and those channels were taken to look at the intensity of the cell outside the cell. So they have a label that's labeled the nucleus and outside. So you have this kind of like marker. This is a labeling techniques to distinguish from those blood cells the type they are. So those are marking 2 different CDs. I forgot which one they are, but CDs are specific markers for cells. And so let's say you have one that is positive for 594 and negative for 647, defines one type of cells. If you have both on, both off, you can see all the combination you basically get. So it's both off, both on, one off, one off, one on. So that's 4 possibilities. So that gives you 4 different type of cells that allows for further clarification. So that's something I wrote recently. So the goal here was to, from this section, I use DAPI for nuclear segmentation because that's a nucleus image. I use 48 is a Z stack for the foci, so that's my spot channel. And then 594 and 647, those are my label for different cell type. Okay. And it repeats itself for the next position, which is position 1. So position 0, position 1, and so on. Okay, so that's the structure. Now let's go into the code. So for that, I'm going to MATLAB. My code is located under imaging. So if I actually look at here, the path is home, gen user, local repo, imaging. And under imaging, I've got a bunch of functions that I wrote. They're really script. So that's one script. So first of all, I turn off the warning because it's really annoying to get warning a bunch of stuff. And I'm first going to load the parameter file. So here, the parameter file, let's look at it. It's also located in the imaging directory. It's already there. Understand human blood param CD7. Let's go there and let's look at that. So mode spot, that's legacy things that are from other code, so I left it there. It first gives the directory where the images are. So as you can see, I get that directory here. Now he asked me for an output directory. So right now I created already one. So for demo purposes, I'm going to do toWell test demo. It will create this new directory, output. It's asking me the name of the plate. It's kind of redundant information, but in case someone saves the directory differently from the plate or the name of the images, that's the option here. You can change that. By the way, it's not tab delimited. All this is just using a space to extract the information. It's asking which channel is the DAPI. So if I bring back, let me try to minimize this a bit. Hold on. If I bring back this guy here, you can see, for instance, that the way we label DAPI is that C00 DAPI. And it should repeat itself over and over, C00 DAPI. So the C0, that's the channel. And so what it means is that the first channel is DAPI. The second one, which is number 1, is AF48. Then number 2 is 594, and number 3 is 647. That's the order by which the microscope were imaging. So DAPI, that's basically the string that will recognize this. Is asking for where is the, for DAPI, we typically use only one section, so I'm asking which one it is, and I said Z0010, which is it, slice number 11. I'm giving the number of channels 3. And then I give them in order, AF48, 594, 647. So all these strings have to match what's in there, by the way. Well, actually, let me rephrase. Number of channel 3, this is the string I use to save my images. So that's the for the output. That's the string you need to use to recognize the input. So there has to be a perfect match of that. Okay. Okay, and then since the 3 channels is asking for some display properties. So here it's kind of important. It's to display the, when I read these images, I project them and I create a thumbnail image. I'll show you in a minute or when we run it. And this requires some prior knowledge. So one way to do this is, let's see, I'm going to pick, I'm just going to pick one, 48. 48 is actually a bit annoying. Well, let's do 48 and I'll take the middle slice. So I can go into MATLAB here and I'm going to just drop the 48 at z equal 10. It's reading this. So that's really what's nice about the deeplib library, is that it has its own display system. On Python, it doesn't work this way. It's not as convenient. And you can basically do linear stretch to see the images. So you can see it's really uneven, by the way. You can see here there's something really funky about the imaging. There's a huge blob. That's interesting. Anyway, linear stretch means that it takes the dimmest spot in the image and turn it to black, and the brightest set it to white. So that thing here, set the stage to white, and something here is black. You can do a log stretch if you want. And we can see that blob again, not too good. I like linear stretch. You can go with a manual stretch and set the minimum. Maybe not so low. But the bottom line is, if you see that for those numbers you see here on the right, 406,000, those defines kind of like the range, so that when we do a projection, I want to be able to compare all my thumbnails with each other. So the only way to do that is to project the image and to save it as a JPEG with the exact same boundaries for min and max, so that if you're above 6,000, it will be white. If you're below 400, you will not be considered. You'll be cropped. That's what that means. So here, let me show you what it looks like once I use that display, because that's the way the JPEG is going to be saved. Voila. So I pick this kind of like, this is kind of a play and error. I typically run the script once and I see how the things look like. I load the images to have an idea of how intense they are. So I put my mouse on this and see the intensity here, you see. And that gives me a good visual. Now, what would be practical is to actually look at something that has a spot. So I could try to read another one, let's say this one here, which is another position. Linear again. Yeah, it's not focused. Hold on. It slices at 17. Okay. $406,000. So that gives you a better idea, and you can see that maybe those guys here are maybe spots. Those images are not the best. So anyway, that's what those number means, and I do that for all three channels. So 488 was the first one, 584 is 400 to 4,000, and the last one 400 to 4,000. Okay, crop 15, that's a new parameters. I just coded it, so hopefully it won't crash on me. But that basically says how many pixels I typically crop each nucleus based on nuclear segmentation, and then instead of cropping it, you know, by having the crop exactly on the boundaries of the mask, I do a dilation of the mask just to get a bigger size, and that's what that is. So I'm putting a 15 pixel boundaries. That's new because the team complained about the fact that for 594 and 647, the stain that they use to identify the cells is not inside the nucleus, it's outside the nucleus. So by cropping too tight around the nucleus, we're missing most of the signal that they want to label them and detect them. So I'm changing this. Nucrad is the number of pixels, the radius of the nucleus based on pixel. That's for these images that you have to play with, otherwise segmentation is going to completely crap out. So 12 is a good number. We play with that for this data set. Same thing. This is try and error. Run the script, see how it looks like. And nuc threshold is a relative threshold. So a value of 1 would mean that you cut pretty much. There's no threshold. You take everything. It's a relative cutoff intensity from the background. So you're 70% above the background by having 1.7 in a nutshell. Max size is basically how small of a pixel. How small, and I know the term is terrible, but how small of a spot do you agree to take? And I authorized all the way down to 1 pixel, big pixel, so very tiny. Can't have smaller than that, 1 pixel. The k-value is the k-value for wavelet. 4 is the right value. You can even pick more if you go to 3. You don't want to go below 3, it doesn't work. K-value can't be below 3, but it's an integer. The higher the number, the more stringent you are, so the more perfect the spots needs to look like. So 4 has always been a good number, and I haven't touched this for years. I'm telling the system that this is a 3-dimensional problem, so that means that it's going to really look for a 3D stack for the foci. That's my filter for the sphericity of my nuclei. So anything above 1.5 is eliminated, and that's the pixel size. Which is probably wrong, but that's okay. Just like I told you before, the nuclear area that is computed for the nucleus, just take it as a relative value. Don't take it as an absolute micrometer square value, because it's not. Okay, that's the parameter. So now let's go and load this. So I'm going to go running off. I'm going to do load the parameters, and then I'm going to ask to see them. So let's see, F9, and it gives you all these parameters now that he entered. So it looks pretty good. It took crop, now crop margin, and now I'm gonna. So one way to do this is you can just call the function here, and it's just crop image. Don't pass any parameters, and it should start doing the work. So what it's going to do, let's go back to the output now. So if I go back here and I look at my output directory here, plate name, out there. So that's my out directory. So let's see if that thing exists. I do Control C, go here, delete this. I don't want to select because it's gonna copy paste when I adjust. There we go. Nemo. It creates two directories, a color image and a crop image. So the color image, let's go there. What it does, it takes each field of view and creates some output. So the first output it does is, that's the full field of view. That's 488. And you can see here the display I mentioned is the one I was telling you, which is that 400 to 6000. And you can see how it's actually pretty well tuned. You see I can see a spot here, I can see a spot here. Those are very clear spots, they're nice and bright. And then others are not so bright. And so, you know, maybe I should go lower than 6000. That's a setting. It's just for display. One thing I forgot to mention in detection, where is that thing? Oh yeah, minimum 1500. That means that any foci that is picked up by the system, the wavelet that is less than 1500 intensity bright will be not considered. It's too small. It's too little of intensity. So that filter will come up later. Right now, it's just showing you, this is my nuclear segmentation and showing to you for the different channels. So that's the channel for the foci. If I go next, that's the channel for 594, and you can see there's nothing there. Nothing is positive. That one is interesting. That one is positive. You can see how that cell is positive. That one is. This, I have no idea what that thing is, but you can see how. And there's some shift here which needs to be improved, but you can see how those stands really look. And, you know, irregular is not circular. So you can see if I were to crop here and compute the intensity, I may miss that positive cell. I don't truly think it will miss it because there's still some bleeding anyway in there. So those will be positive cells most likely. And those will be completely negative. Next is the DAPI. So that's DAPI, that's my pattern. That's what I use for nuclear segmentation. And you can see that those are really beautiful and they have a pattern. They're not really fully, you know, if I were to zoom on it, let's see if I can zoom more, maybe less. You see this pattern, how beautiful they are? And you can see how those cells look very different, nice and spherical cell versus like deformed and bigger, different intensity. That's probably a cluster of cells, frankly, looking at it. So that's unfortunate. That definitely looks another cluster, two cells one on top of each other. So those are things that, you know, I don't break it down. It's too complex for me to do the segmentation for that. We need some clever system. My system is pretty good. It does wavelet and things like this, but okay. That's field of view 1, then it repeats for field of view 2. You can see that cell's got a tons of spots, some spot, and so on and so forth. So that gives you an overall view. Okay. And then what the system does, if we go back here, it's actually, so if you look at the code, it's very simple. I read the image, by field of view for each field. Oh, and there's an output on MATLAB tells you where we are. So see, it's like it's a reading, cropping, statistics, blah, blah, blah. So you have an output. So it tells you how many nuclei it kept. So it does a segmentation. Then the 58 out of 75, that's based on the P2O filter and also the intensity cutoff that we have. Or size, sorry. I have a size filter on this for the nuclei. The size is based on some average from the whole group. I'm sorry, no. The filter for size is based on the nuclear radius. Let's see where it's at. Right there. So you have the nuclear radius, which is then I do pi nucrad to the power 2 times 75%. That's my size cutoff. And that basically allows to get rid of small debris that would be picked up as nuclei. So I do a cutoff by the sphericity, P2A, and the cutoff. And that is located somewhere here. So let me go back. I read the field, I do the segmentation here, and then the parameter for segmentations are right there. Then I use a function that is awesome in Deep Leap called measure. So the way the function works is you pass first, well, in this case, I'm only doing one measurement. I'm passing the mask. So it's a Boolean. And I'm asking measure P2A and the size on this mask. And so it will create MSR world, and I have a bunch of measurements. And then for each of these measurements, and the way you read these measurements is you do a loop on the number of nuclei. So I do the measurement, I look at the size of this array, which is somewhere, number of cells here, the length of MSR, and then I do loop on the number of nuclei, 1 to number of cells. And basically you can see here my filter, it's less than P2A mean, and the size has to be bigger than the cutoff. And if that's the case, then I say keep the nucleus and crop all the other images. So what I do is I crop the DAPI first, which is the nucleus image. It's only a 2D image. So I have a function, I have a cool function that I wrote called crop from mask. I give it the initial image, I give the mask, and I say mask equal iNuc, so it only keeps one nucleus, and then he crops it. And then it saves the coordinates. So I save the array of coordinates for each nucleus for one field of view, and I put that into that coordinate array. Once I'm done, I'm going to now read the other channels, and I'm going to crop them the same way. And I check for the other channel. If there are 2D channels, I just crop in 2D. If there are 3D channel, I crop in 3D. So there's a little trick here, which is here size. If it's 1, do it in 2D. If it's more than 1, do it in 3D. And I also save, so I save those display. So those time color images are saved right now, as you can see. And so they are saved into a different directory. So right now I'm still, I'm saving a couple of things here. The crop image are not here. The crop image are going to be here. And so now I'm generating, and that's going to be what we're going to use to do the spot detection, only on the stacks for the ICS. So you see it's pretty big. List view. I just want to show you the structure on this one. It's taking a while, so why it's doing this. And then at the end, I save the statistics into an array, which is called MSR group cumulative values. And then when I'm done with cropping all the images, I dump the full cumulative array into this nucleus statistics CSV, which is going to be located in the crop images. So that's when it's done. Now, is it done? It's the problem. It's when there's a lot of images, it takes forever. So while it's doing this, I'm going to continue walking you through the code. So once I finish this, I save into that into that file nucleus statistics all the stats, and then finally I have this last loop is basically this is the spot detection, which requires, you know, what is your let's see, that's your output direct, that's where the images are. So I say it's into the crop images. So he's going to take all the crop images in that crop images directory. He's going to use the parameter file that I created. This is chance string is basically a repeat because it's in param, so it's kind of redundant, but that one has the actual name of where the channel for the spot. So something that could be removed because it's, like I said, it's completely redundant. It's already in there. And that parameter is something else that I can walk you through quickly, which is oh yeah, it's a print flag, so it's just to print a bunch of output. Okay, I don't know if that thing will ever show up, but in a nutshell, that's the way the code works. So since it's still thinking, let's go visit this guy. So to go visit something, you do a Control D. And it should take me to this guy right there. Here we go. So that's the code. That has some dependency that you should have. So all the functions that are using there are in imaging directory, so you should be fine. The most important one is the spot detection. So it's called James spot detection. So James was my student at Berkeley. And then if we go look at this one, I'll do again. So you can evaluate selection is F9, or if you want to open, Control D. And because it's still working, it's kind of not responding. Or did I crash the system? I may have crashed the system. I think for demo purposes, I can kill it. There we go, Control C. So I kill the compute, and you can see the function here. That's calling more functions. There's a weblet somewhere, web at who, where is it? I just, just look at that. That's what I would like to recode in Python. That's this whole spot detection is there. But maybe we can do even better with other AI tools. So that's where we are with this. But I think I gave you quite a bit already there. So let's walk through what we got. This is dead. Yeah, it's not happy. So I killed it. Sometimes it's better to just go in command line instead. Where's my command? Okay, so let's go to data. Let's go to process. That's where the things are listed. ls cd2 859, the demo one, 2 test demo. And we have those two directories, crop and color. If I go into crop, now the bad thing is because I killed it, I don't have my output file. It's kind of unfortunate. So I've got all these, cd crop. See, it's all the mask and TIFF, but there is no, I don't have any output. So let me show you the output, what it would look like. I'm going to run this manually. Let's say I'm here now, and I'm going to save whatever it did. F9, and now I should see, if I do ls again, sorry. Voila. And so if I do vi, of course, star CSV, that's your output. So it's kind of complicated. I have the field name, the well. So field name, the well is A1. Position is position 1, ID 1. And then I have size. So size is 837. Then I've got the P2A 1.06. And it gets interesting. I have the mean DAPI, the sum DAPI, the standard deviation for DAPI, and I repeat that for each channel. Okay, so that's the first output. Very grotesque at the nuclear level, but that I created this. That you won't have in if you're using the benchmark that I said. That's new. I created this recently. So, oops, just did something. Escape, shift, Q. Oh, crap. I don't know what I'm doing wrong. Shift Q, Q. Why is it not taking this? I don't know what that VI version is. It's annoying. Escape. Okay. What else? Okay. So now we're done. If I go back to that crop images, we have a bunch of images. And what he's going to do is going to read the ICS file and the mask and the DAPI and process. So now if I just go like that and do F9, it says QC file was not found, but it's trying to run things. And now if you look again here, I just created a subdirectory that is called something process. It's really annoying why they have this slash here. There must be a mistake somewhere. I gotta change this. So under foci process, you can see the spot detection is taking place right now. So let's go there actually because it's easier if I show the output directly. Should I want that? Okay. Come on, give me that. Okay, that's the output. So you can see the output is pretty convenient in Linux because just like MATLAB, so Windows, that's the display with the 406,000 display, like I was saying. So you can see in white and in blue is DAPI to see the nucleus and how the nucleus was contoured with the segmentation. So did a pretty good job. You can see how it's not picking any of this crap here. None here too. So maybe I have a very stringent detection. But here on the other hand, you can see how it got these spots. Here, nothing. Here, you got 2 spots. So sometimes when people use my tools, like, oh, why did it pick that and why not? That's kind of like the magic of Weblet. They tend to look at the K value is what makes a difference here. If he sees a spot that looks really nice, he will pick it up, even if it's not so bright. Because he increases the value of the Weblet itself, the value itself goes up for some reason. So you see those are pretty dim. They still are nicely picked up because you have very well-defined spots. So you can see how those ones, for instance, were rejected, but those ones were kept. Now it's, it's a setting. You can change this if you're not happy with it. And, I didn't tune it too much. I think it's doing a decent job. It's never perfect. Human eye is perfect. We're not. See here on stuff like that, if you were using a threshold here, it would be a disaster. It would pick up tons of crap. With the Weblet, it's resisting. But I would actually eliminate those guys. They're clearly full of crap. That on the other hand, for some reason, he decided to pick it up. Anyway, so you can see the output here. Is it still running? I think it is. And as it runs, it creates this output file that we discussed, the nuke summary file and the foci summary. And so if I, if we go back here and look at the output, that was one last thing. You should have some listing of what it creates somewhere. Where is my? I'm looking for the where I save the output data. Here we go. Nuke summary. F-close. Struct sprint. So that's this guy here. Of course, this is not going to let me look at it until this is done. So I'm going to kill it. And now I'm going to do Control D. Yeah. I didn't know. I'm wrong. Oh yeah, the header is here. F edge. Nuke sum F edge. So nuke sum F edge. It's been a long time I haven't looked at this, so apologies. Control F, nuke. File header. Let's see. Previous. I forgot. I don't know. to be looked at. Mm, it's just opening. It's just the output file. Yeah, it's just the ID. I'm wrong. Um, where is the header? Oh, flag first here. Print header with output if first time run. So that's right. Let's say it's process string. That's the value you want to look for. Let's see. Find previous. No, I'm wrong. So much for a demo. Okay.